let's work through a few more examples that are going to demonstrate some of the problems that we can encounter with limits. So here we go. The limit is x approaches 0 for the absolute value of x over x. And we could graph it if we wanted to. There's really not much algebraic manipulation that you could do with this. You could write it as a piecewise function, but I'm not in the mood. I am going to make a table. And the thing I cannot use is a 0. I don't know why I put it in a speech bubble, but there it is. So I want to know what I'm approaching down here. And as I approach 0, I'm going to sneak up on 0 from the left and from the right. I'm going to get closer and closer to it. So super close to 0, maybe a tenth. And then a 100th, and then 1/1000th. And that's from the positive side. We'll come at it from the left, so the negative side. So negative 1/10th, negative 1/100th, negative 1/1000th. Let's put a 0 in there, a decimal in there. There we go. And we can do this one in our head. I'm not even going to grab a calculator yet. I do want to show you the graph in a minute. It's kind of cool. And if I was to plug in negative 0.1 here, I would have negative 0.1, which becomes positive, divided by negative 0.1. So I have positive divided by negative, but it's the same number, the same value, same quantity in a sense. There we go, negative 1. The same magnitude, I guess I should say. So if I plug in a negative 0.01, I would have positive 0.01 divided by negative 0.01, so negative 1. And the same thing here, actually. So anytime I plug in a negative into this function, I'm going to have a positive divided by a negative, so I get a negative. And I will get a negative 1, again, because I'm dividing basically the same number over itself, just with different signs, same magnitude. But if I plug in a positive, I'll have positive 0.1 divided by positive 0.1, so I get a 1 and a 1 and a 1. And so as we approach an x value of 0, the y value that we're approaching, well, I'm approaching a negative 1 from this side because it is negative 1. I'm approaching positive 1 from this side because it is positive 1. And as I do so, I'm approaching two different values. I'm not even going to grab a calculator. I said I might just to graph it. I don't need to do that. Here we go. There's this side, and there's this side. But the function does not exist at 0, so that's why we have an open circle there. And because of this, because we're approaching two different values, the limit does not exist. So the limit, took all this blank space just to write the limit does not exist. Does not exist. And here's a shortcut that I believe you saw a little bit earlier. I think I wrote it down on the very front page when we did these notes. No, I did not. Okay. Abbreviation for that, DNE. I'm looking back through my notes to see how I wrote it. DNE means does not exist. So I will not write this sentence anymore. I will just put DNE, and everyone knows what that means. That's perfectly good notation on any exam. So let's move to the next problem. And I hope you realize, again, direct substitution is not going to work, and there is no level of algebraic manipulation that's going to make that happen. So I am not going to be able to simplify something and then be able to plug it in. Just not going to happen. I wish, but it's not. So what I am going to do instead is, well, make a table of values. And I hope with this example, you will see why we approach from either side rather than just pick a number close to it, because we need to see the pattern as we get close to it. And in this case, the pattern is going to become fairly obvious that the limit will not exist. There. Now you know the answer. Ha ha ha. But before we move on from it, let's do it. Negative 2 is what I'm aiming for in the little speech bubble that you will not see in any textbook, but I just like to put it. So I'm going to sneak up on a negative 2 from the left. We're going to sneak up on negative 2 from the right. And we will use a calculator. So here we go. As I type this in, keep in mind that the denominator needs to be in parentheses. There we go. Now you can see it. And we're going to go to the table. We're going to clear out anything that needs to be cleared out over here on the X side. There, those are cleared out. And we're going to plug in these values. Let's just type them first. Oops. We'll look at the values later. Pause the video if you need to. This is what I have. I am going to write these down on the paper just so I can really see what's happening as I approach an x value of negative 2 from the left and right and find out what the y value is that I am getting closer to, if I am. I'm not. Negative 10, negative 100, negative 1,000. This one coming from this side is 10, 100, 1,000. That's what I have. That's what I'm dealing with. And at this point, I realize that when I am approaching an x value of negative 2, my y value is not approaching anything specific that I could nail it down to. Now, here we are approaching two different values. Here we are decreasing without bound. So this is like negative 10, negative 100, negative 1,000, negative 10,000 if the pattern continues. This one is going towards negative infinity. This one's going towards positive infinity. And the reason why is because of a vertical asymptote that takes place at x equals negative 2. So if I was to graph this, a very rough sketch, but if I was to graph this, it would look like that on this side. Again, very rough sketch. Not doing the best job with it, but that's it. And so when I approach an x value of negative 2 from the left, we're going way down here. Approach an x value of negative 2 from the right, we're going way up here. And so we're not approaching a specific value. We would say that this one increases or decreases, actually both from either side. Decreases without bound, increases without bound because of the vertical asymptote. All right, let's crank out a couple more examples that are going to be amazing and fantastic. You're going to love this. Here we go. This next one looks almost exactly the same as the one that we just did, but it is slightly different in that we are squaring the denominator. So let's do the same thing, only we're going to square the denominator. So there we go. We have that typed in now. I'm going to make a table again. If you're tired of writing the same values over and over and you want to watch, that's totally fine. Although I do recommend that you write something down just so you'll have a reference for it later. But obviously I'm looking for a negative 2, but can't directly use it. So negative 2.1, negative 2.01, negative 2.001. There we go. We're going to have negative 1.9, negative 1.99, negative 1.999. And we will see what happens at the table. We already have these numbers in there from a minute ago. I hope you're noticing this scientific notation. This is 1e6, not the e like Euler's constant, like 2.7, but e as in like times 10 to the, that capital E in this context is an exponent, like times 10 to the whatever. So 1 times 10 to the 6, which we see down here is a million. Okay, so let's write that down. So this is 110,000. This is 1 million. This is also a million. This is, 10,000. And this is 100. And so we have a couple options here for what we could say this limit is. So let's follow along. As we are approaching an x value of negative 2, the y value is approaching, I could say infinity on this side and infinity on this side. And that would be correct. So the answer to this one is infinity. That's a very strange infinity. This side is way bigger than that side, but whatever. It's like a snowman got pushed over. So I was about to draw it, but we'll leave it. We'll leave it as an infinity that looks bad, not a sideways snowman. But we are approaching infinity and infinity. Now, infinity is not a number. Infinity is a concept. Infinity is an idea. So we could say that this limit is infinity. Yes, it is. But it is very much acceptable to also say that this limit does not exist. Either one is acceptable because you can't count to infinity. You can't get to infinity. It is more of a concept than a number. But because we are approaching, because these are both increasing without bound, they are both approaching infinity. But in this case, this is the previous example, this one was decreasing without bound, not as fast as the one that we just did, but this one was decreasing without bound, that one's increasing without bound, so they weren't even approaching the same direction. So that's the difference. Okay, this next example is my favorite limit example ever. First time I graphed this, I thought my calculator was messed up. I love this one. First of all, direct substitution is not possible. Plug in a 0. We've divided by 0. We have sine of 1 over 0. What is that? I don't even know. So let's type it and see what happens. the sine, we were in radians, by the way. You should just stay in radians. 1 over x, and we will go to the table. I'm going to delete these numbers in here. And I'm not going to make a table on paper, and you can if you want, but I'm not. I am going to make the table on the calculator, and I also want to show you some things on the graph. So let's sneak up on a 0. So let's sneak up on a 0 from the left. We're going to go negative 0.1, negative 0.01, negative 0.001. Okay, whoa, wait a minute. I'm looking for patterns here. I'm pattern sniffing. 0.544, 0.5064. And at this point, by just looking at these first two entries, these first two y values, I might say, oh, we're approaching 0.5, so 1/2, right? Okay. Well, then I get to negative 0.8. Well, let's go further. 0.0001. And then we're up to 0.3. Like, what? This is not converging to, and that word's going to come in handy later, but this is not converging to a logical number that is rounded to a specific value where I would say, oh, look, it's 1/2. It's not. It's all over the place. So if we even get closer, now we're at 0.35. So is it 1/2? Is it 0.3? Is it 0.35? Is it negative something? I don't know. If we tried this from the other side, and I'm going to kind of go backwards so we can sort of pinch it in the middle and see. So I'd have 0.0000. I'm losing track of it. How many zeros did I have on that last one? 0, 1, 2, 3, 4. Yeah, there we go. And then 0.0001, 0.001, 0.01, 0.1. Okay, so I am going to approach a x value of 0 and see what y value I logically approach. Well, it's all over the place. There is not a pattern as I do this. Why don't we look at the graph? This is great, y'all. You're going to love this. May I highly recommend that even after you see this video and you watch this being graphed on a graphing calculator, please, for your own mathematical enjoyment, type this into Desmos. Please do. And then zoom, and zoom, and zoom, and zoom. It is so worth your time. I promise. Okay. Functions typed in. We're going to graph. I'm going to graph it on a standard window, so a little bit of calculator literacy here. Let's press zoom, and I'm going to go to a standard window, which is, in the calculator, is from negative 10 to 10 on the x-axis, negative 10 to 10 on the y-axis. On paper, I have this from negative 5 to 5 and negative 5 to 5, but we'll be all right. Okay, so far so good. We're doing great. And whoa, what was that in the middle? What in the world? I don't know. Well, I want to see what happens at 0 because the table told me nothing. So I can't direct substitute. I can't use algebraic manipulation. The table was absolutely useless. And now I'm stuck looking at the graph and I can't see what's happening at 0. So why don't we zoom in? I'm glad you said that. I just pressed zoom. I'm going to go to zoom in. And wherever your cursor is flashing, that's where you can zoom in. If you want to move it around, you can, but I'm centered at 0, 0. I'm going to press enter because that's where I want to zoom. So let's see what happens. And what is that? What in the world? Huh? That doesn't work. Well, let's zoom in again. Zoom in again. Get ready. What in the world? Okay. This one, no matter how much you zoom, and again, try it on Desmos. No matter how much you zoom, you're going to have a mess. I'm going to zoom in one more time. And when I do, my calculator is getting into territory where it doesn't, see, isn't this fun? Where it doesn't quite know what to do with it, because the closer I get to 0, the more, I love this phrase, the more wildly this function oscillates. Oscillates means it goes back and forth. And so I could zoom in all day as much as my calculator would allow, and it would never show me anything clear that happens at 0 because nothing clear happens at 0. It's just going to get wilder and wilder the closer we get to 0. It's the nature of this function. So if you wanted to graph it, and this is going to be the most jacked up graph I've ever drawn, it doesn't even look like it passes a vertical line test, but that's kind of the point. We can't even see what happens. So this one does not exist, which leads us to 3 times that a limit will not exist. We have actually just explored these 3 things, and here they are, in no particular order. Well, actually in the order in which we discovered them. 3 times a limit will not exist. Time number 1, if the limit from the left does not equal the limit from the, I'm going to run out of space, from the right. Okay, there is a notation for this, and I want to go ahead and introduce it to you now. In a few lessons, you're going to use this notation a whole lot more. But the limit as x approaches some value. What value? Okay, most of the time in calculus, when we just want some random x value, we don't use x, we are using x in other contexts. So we're going to use c, like just some random constant that is an x value. The limit as we approach c from the left, it looks like an exponent. Notice it's not in the front, it's at the end, and it's up and kind of floating, of our function, does not equal the limit as x approaches c from the right of our function. That's time number one, that a limit will not exist. Here's time number two. If the function, let's spell it correctly, increases or decreases without bound. And that is where we would say it approaches infinity. So this is that option we had a couple problems ago, a couple examples ago, where we could say, oh, it was infinity, Sideway Snowman, or it does not exist. And that's the case. Now, again, if the function has a vertical asymptote where the two ends of the asymptote are going in opposite directions, then it truly does not exist. The limit would not exist. There is no option to say that, oh, it's infinity or it's negative infinity, because it's doing both. And then the third one is the one you just saw. And I have never seen another example of this, but it's worth showing you because that's just such a good example. If the function, love this phrase, oscillates, I got this out of an old textbook, oscillates wildly, wildly oscillating function. And it would, to be more specific, it needs to oscillate wildly at the point where we're trying to figure out what happens. Because I could technically, I'll slide back down in a second, I could find the limit as x approaches 1 of sine of 1 over x, because I could plug in a 1. But if it oscillates wildly at the point where I'm trying to figure out the limit, then we have a problem. So just oscillating wildly is not bad, but oscillating wildly at that point. And same goes for this one. The function can increase or decrease without bound, but if it is at that point where I'm trying to find the limit, that's when the limit will not exist, not the function.